Dear students, in last class we studied visual critical disruptive voltage and also we solved an example on visual critical disruptive voltage. Today you will be learning corona loss. Around a conductor there will be some ions and air molecules will also be present there. These ions will accelerate when the voltage at which the conductor is operating increases beyond certain value. When these accelerate, they will collide with the other molecules in the air and they will dislodge electrons from those molecules. That means the increase in voltage at which the conductor is operating will result in transfer of certain energy to the ions, and this transfer of energy to the ions is referred to as loss due to corona. It is referred to as loss due to corona, and it is treated as the resistive loss. It is treated as the resistive loss. And there is no derived formula available for calculation of corona loss. Several researchers have worked on corona loss and given empirical formula based on their experiments. Mr. Peake gave one empirical formula for corona loss under fair weather condition, and then Mr. Peterson gave another formula to calculate corona loss under foul weather conditions, and Mr. Peterson gave another formula for calculation of corona loss under foul atmospheric conditions. We'll study these formulae and also we'll solve one problem based on these formulae. But before that, we'll write the definition of corona loss. The ionized particles near the conductor surface take energy for accelerating and dislodging electrons from air and other gas molecules present near them. This energy taken by ionized particles is called as corona loss and is treated as resistive loss. There are no derived formula for calculation of corona loss. Several researchers have given empirical formula based on the experiments for calculating the corona loss. Peake's empirical formula for corona loss under the fair weather condition is PC equal to P stands for power, C for corona. So corona power loss formula it is 241 into 10 raised to minus 5 into F plus 25 by delta under root R by delta into Vp minus Vc whole square kilowatt per phase per kilometer. Where Vp is phase 2 neutral voltage and F is frequency of operating voltage. For storm or foul weather conditions, the value of critical disruptive voltage is taken as point 0.8 times Vc. So with this value of visual critical disruptive voltage, the formula for corona loss becomes 241 into 10 raised to minus 5 into F plus 25 divided by delta into under root R by delta into Vp minus 0.8 Vc square kilowatt per phase per kilometer. Please know that if the length of the line increases, the corona loss will also increase, because there will be charged ions to take energy from the conductor throughout its length and around it. Using Peake's empirical formula for calculation of corona loss, we can calculate the corona loss approximately if and only if certain conditions are met. In other words, we can say that the Peake's empirical formula has got certain limitations. And what are those limitations? First one, corona loss is predominant. It means that if corona loss is considerable, not very small in magnitude, then only we can make use of Peake's empirical formula. Secondly, the operating voltage frequency must be between 25 Hz and 120 Hz. If frequency is less than 25 Hz or more than 120 Hz, then Peake's empirical formula will not result in the correct value of corona loss. Third one is the ratio of Vp to Vc should be greater than 1.8. Vp is what? It is operating voltage of the conductor with respect to neutral. Vc is critical disruptive voltage. So ratio of these two should be greater than 1.8. Then only we can make use of empirical formula. Otherwise, results will not be useful to us. Fourth one, the radius of conductor is greater than 0.25 centimeter. If the radius of conductor becomes less than 0.25 centimeter, then once again empirical formula given by Peake will not give us the good results. We have to keep all these points in our mind while using Peake's empirical formula for calculation of corona loss. So if weather condition is fair, we can make use of Peake's formula. If weather condition is not fair, if it is stormy or foul, then we can replace Vc by 0.8 Vc and we can make use of Peake's formula. But if the ratio of Vp by Vc is not greater than 1.8, say it is less than 1.8, then what to do? For that, Mr. Peterson has given a formula. So now we'll write Peterson's formula. This is also empirical formula only. Peterson's formula for calculation of corona loss when Vp by Vc is less than 1.8. Corona loss Pc is equal to 1.11066 into 10 raised to minus 4 into F into V square by ln of d by r bracket complete whole square into F kilowatt per phase per kilometer. Where F is the factor which varies with the ratio Vp by Vc. Typical values for different Vp by Vc in fair weather conditions are, we'll write these typical values for different Vp by Vc in table. Vp by Vc and F values table is here. You can just note down this table. Now we will study some advantages of corona loss. See, we can have the voltages that increase very slow or very fast with respect to time. For example, I will plot here RMS values of voltages versus time. The voltages may slowly increase like this, or the voltages may increase this way, or the voltages may increase this way. Here you can see plot of Vrms versus time. Say this is V1, V2, V3 now. You can observe here V1 is increasing slowly, V2 is increasing faster than V1, and V3 is increasing very faster than V2. That means rate of rise of V3 is more than rate of rise of V2 and V1. If you see this part, it appears to be having very high positive slope. That means in less time, voltage rise is more. V3 is said to have here a steep rise in its value. And such voltages are very dangerous for the appliances and for other components of power system. It may be line insulator, it may be insulator used in transformers, insulator used in circuit breakers, or any other component you take. Wherever insulation is there such voltages prove to be very dangerous because they can puncture the insulation. The corona works in a way the safety valve in a cooker works. That is, in the event of high voltage steep waves due to switching or lightning surges, the corona occurs and the energy in the lightning surges and switching surges gets dissipated in the surrounding air. The dissipation of energy in the switching surges and lightning surges protects the various insulators used in the power system. So I'll write that here. The advantage of corona is that it works as safety valve in the event of high voltage steep waves due to switching or lightning surges. The energy of these waves is dissipated in air as corona loss. Next, we'll take up disadvantages of corona. The first disadvantage is corona loss. As we have studied earlier, corona loss or any other loss will result in reduction of efficiency of transmission line. So, corona loss is definitely a disadvantage. Second one, whenever corona occurs, the communication systems will be having interference. That is, if you are using an audio system or a video system, you will find some disturbance there. Factors affecting corona loss. The corona loss is affected by the physical state of atmosphere as well as by the conditions of line. The various factors that affect corona loss are, these all things we have already studied, but just we are listing them here. Number of ions, size and charge per ion, mean free path available for ions, line voltages, ratio of distance between the two conductors to the radius of conductor, state of conductor surface, whether it is clean or unclean. Lastly, shape and size of the surface. That is, whether the conductor surface is cylindrical or rectangular, and the size of the surface is large or small, etc. Now we will solve one problem based on the disruptive critical voltage for visual corona and the power loss due to corona. Find the disruptive critical voltage and critical voltage for visual corona of a three-phase 50 km long line consisting of SESR conductors of area 240 mm square spaced in a 3.5 meter delta arrangement. Diameter of conductors is 2 cm. Temperature is 27 degrees Celsius and barometric pressure is 73 centimeter. Assume M equal to 0.85 and MV is equal to 0.72 if the line is operated at 132 kV. Find the corona loss. What will be the losses in a fair weather and in storm if the line voltage is 220 kilovolt? Solution. First we will write given quantities. length of line comma L is equal to 50 kilometer. Area of cross section of conductor capital A equal to 240 mm square. Distance between conductors D equal to 3.5 meter. Here conductors are placed as vertices of an equilateral triangle with side length equal to 3.5 meter. Diameter of each conductor D equal to 2 centimeters. Therefore, radius small r is equal to 2 by 2 equal to 1 centimeter. Temperature is given as 27 degrees Celsius. Barometric pressure B is given as 73 centimeters. M is 0.85 and MV is 0.72. We have to find critical disruptive voltage, visual critical disruptive voltage, corona loss at 132 kV operating voltage, and corona loss at operating voltage equal to 220 kV, and fair weather conditions. Lastly, we have to find corona loss at operating voltage equal to 220 kV and stormy conditions. We know that the maximum gradient at the surface of conductor G naught equal to 21.1 kV RMS value it is per centimeter. We will calculate air density correction factor. Air density correction factor delta 3.92 B divided by 273 plus T that is equal to 3.92 into 73 by 273 plus 27 degrees Celsius. Simplifying, we get 0.953. Therefore, critical disruptive voltage Vc equal to R into G naught into M into delta into ln of D by R, that is equal to radius is 1 centimeter, so 1 into G naught is 21.1 kV, M is 0.85, put it in bracket, into 0.953, just now we have calculated, into ln of 350 centimeters. We have to convert meters into centimeters here. By radius 1 centimeter. Simplifying, we get 100.12 kilovolt RMS. This value is RMS value. Next we have to find visual critical disruptive voltage, that is VV equal to 21.1 into MV into R into delta into the bracket 1 plus 0.3 divided by under root R into delta, bracket complete, ln of D by R, unit is kV RMS. 100.12 kV, that is Vc value is also RMS value here. Substituting the values 21.1 into 0.72 into radius is 1 centimeter, 1 into delta is 0.953 into the bracket 1 plus 0.3 divided by under root 1 into 0.953, bracket complete, ln of 350 centimeters divided by 1 centimeter. On simplifying, we get VV is equal to 111 kilovolt approximately. The line value of Vc is equal to root 3 into 100.12 kV, that is equal to 173.20 kV. The line value of visual critical disruptive voltage is equal to root 3 into 111, that is 192.25 kilovolt. Next we will calculate corona loss. First one, at operating voltage Vp is equal to 132 kV by root 3. Pc is equal to 241 into 10 raised to minus 5 into F plus 25 divided by delta into under root R by D into Vp minus Vc whole square, that is equal to 241 into 10 raised to minus 5 into, assuming frequency as 50 Hz, 50 plus 25 divided by 0.953 under root 1 divided by 350 into 132 by root 3 minus Vc. Vc calculated is 100.12 whole square. On simplification we get 5.79 kilowatt per phase per kilometer. Second one, Vp equal to 220 kilovolt by root 3. For fair weather condition, Pc equal to 241 into 10 raised to minus 5 into F plus 25 divided by delta under root R by D into Vp minus Vc whole square. That is equal to 241 into 10 raised to minus 5 into 50 plus 25 divided by 0.953 1 by 350 into 220 by root 3 minus 100.12 squared. On simplification we get 7.33 kilowatt per phase per kilometer. In third part we have to find again corona loss at Vp equal to 220 kilovolt by root 3 for stormy condition. PC is equal to 241 into 10 raised to minus 5 into F plus 25 by delta under root R by D into Vp minus 0.8 Vc whole square. Substituting the values, 241 into 10 raised to minus 5 into 50 plus 25 divided by 0.953 into 1 by 350 into 220 by root 3 minus 0.8 into 100.12 squared, we get 22.30 kilowatt per phase per kilometer. These PC values, if we multiply by 3 and the line length, we get 3 phase total power loss for the given length of line. That you can take as homework. Dear students, now I will stop the class and continue in next class. Thank you.